Well, welcome everybody. I'm super excited for this. Let's dive right in. This is a project that I was working on over the summer. I was absolutely fascinated by AlphaGo and AlphaZero, and had the opportunity to implement it from scratch, and I learned a ton. And here's a lunch and learn to just share some of my experiences. So back in 2016, DeepMind, which I'm not sure if it was part of Google back then, but the AI research team, they released AlphaGo. And AlphaGo was the first AI that actually outperformed humans at the game of Go. And this was a pretty big watershed moment in the history of AI, because Go has been notoriously known to be this really complex game. And for reasons that I'll describe in just a second, it was really difficult, close to impossible for machines to reach like true grandmaster level performance. And so this threshold was reached in 2016. And Lee Sedol, who's the Go like #1 player at the time, who ultimately lost to AlphaGo, had such a crazy experience in the process of playing. He said stuff like, "It made me question what it means to be human," and even ultimately retired from Go because of this defeat. He just felt that the game would just ultimately be transformed by Go engines, and so it was a pretty crazy time. That was very quickly followed up actually with AlphaZero, which is an AI that basically uses the same exact architecture to solve the games of Go, chess, shogi, and other related games where you can imagine you have perfect information about the state of the board. So the whole board state is known. There's no like unknowns like in poker. For any game that's like that, the AlphaZero structure can more or less systematically solve that game. And importantly, it can solve that game using the process of self-play. So literally just by experimenting within the confines and the structure of the game itself, it's able to learn strategy and reach superhuman performance and really just sort of systematically improve generation after generation. And so when this finding came out back in 2017, I was absolutely blown away. The idea that a system could simply just self-learn, as opposed to AlphaGo the year prior, it was definitely a watershed moment, but it was definitely trained on Grandmaster Go games. AlphaZero, on the other hand, was able to surpass AlphaGo's performance, but it had no human training data involved inside it at all. So I just found that to be absolutely remarkable. In fact, it actually kickstarted a lifelong obsession of mine where I've just become very addicted to chess. It was literally because of AlphaZero that I got super into chess. And so in sort of being fascinated with this, I didn't really truly understand how it worked. And so this summer I wanted to implement AlphaZero. And so I wanted to do it on a simpler game, because ultimately the architecture and the approach is the same across all of these games. So I decided to do it with Connect 4. And so this talk is about how that architecture actually works. So in order to describe how to win or solve games like this, you have to understand first this concept of a tree, natural structure inside of computer science. And basically the way that it works is we represent board positions as nodes inside of this tree. And so the starting position or the root position is up here at the top. And then from this position, there can be any number of moves. And so we represent these moves as arrows over here. And the arrows point to subsequently other positions, and then other positions can have even more arrows. And this process continues all the way down until you reach the bottom of this tree, where we have what's called terminal nodes. So terminal nodes are nodes where the game ends, and it ends with what we call a reward that we denote by this variable called Q. So Q can either be -1 if the game ends in a loss, it can be 0 if the game ends in a draw, and then 1 if it ends with a win. And so you can imagine every game that has a finite structure, like all of these games, ultimately create a finite tree over here that in principle can be enumerated. But this is where it gets a little bit tricky. So our goal as an AI or developing an engine is to essentially find a path from the root node over here all the way down to a terminal node in a way that actually maximizes the likelihood of reward. So maximizes this Q variable down at the bottom. So this is where it gets complicated. For the game of Go, there's actually 10 to the 170 unique Go positions, as compared to about 10 to the 80 atoms in the observable universe. Like this is such an unfathomably large number. Like if you had an entire universe worth of atoms, for every single atom in the universe, you would still be 10 orders of magnitude shy of being able to count the number of unique positions in the board game of Go. So it's just uncomprehensibly large. And that basically means that brute force is impossible. So we definitely cannot enumerate this tree on paper or in RAM or in any computational system, really, right? So instead, we have to explore subsets of this tree or subtrees. And we have to explore those subtrees intelligently. And what I mean by intelligently is that there's certain moves that you all know in board games where it's obvious that the move would be ridiculous. And so it's worth no further exploration whatsoever. And we as humans develop this intelligence or this intuition about which moves are sort of straightforward to discard. And so the goal here is to develop that intuition or develop that intelligence so that we can quickly discard certain subtrees in favor of other subtrees that are perhaps more promising. And so this process is called tree search, where we literally explore the tree. And for those of you who are familiar with some computer science tree search stuff, the sort of old school methods of AI of like breadth first search, depth first search, you may have heard of minimax or alpha beta pruning. They kind of won't work for trees that are just this large. And that's the reason why it took until 2016 for us to actually beat grandmasters at the game of Go with computers, because our old school methods of minimax and so on just weren't working for this game. And so the alternative approach that the AlphaGo or AlphaZero team took to exploring this tree was this tree search called Monte Carlo tree search, or MCTS for short. And this is really just the crown jewel of AlphaZero. It's this really beautiful algorithm that once you understand it, you're not only blown away by the simplicity of it, but it's just the foundation that enables this kind of intelligence to manifest. And so this talk is going to explore what Monte Carlo tree search is and how it works. But before we get to that, we have to discuss first a simplified version of Monte Carlo tree search, which is called the multi-armed bandit problem, which is an absolutely fascinating problem. And the way this problem works is, let's say you're at a casino and there's a bunch of slot machines, and you've been given some intelligence that some of these slot machines are actually rigged in your favor. And that's to say that their average payouts are slightly larger than the typical slot machine, which on average loses over time, of course, right? But the interesting thing is that you don't know which machines are rigged or how rigged they are. Is it 5 machines that are rigged? Is it 1 machine that's way better than all the rest? So you don't know like what the level of riggedness is, I guess you could say. But despite that, you have a finite number of coins, and your goal is to maximize your profit. And the other interesting curveball here is that despite some machines having a sort of on average tilt towards your favor, there's still a degree of randomness to these machines, meaning you can spin a machine, and if the machine actually wins, you don't know definitively that that's a rigged machine. That might have actually been a losing machine, but just by chance, you happen to get the spin that actually won. And the inverse can be true as well, where you might actually lose, and it would be sort of hasty to conclude that single loss actually dooms that machine to being permanently bad, because you might have just lost by random luck, and that machine might actually be the best machine, right? So there's this inherent randomness still to these machines, but there's an established average win rate for some of these rigged machines, and your goal is to find these machines and then exploit them. And so inherently, this multi-armed bandit problem is this fundamental balance between exploration versus exploitation. And so exploration is this idea of using your finite coin budget to gain information about the riggedness level of each machine. And then exploitation is basically saying, based on the information that you have, let's just exploit the machine that you believe to be the best machine so far. And so it should be clear to you that these objectives of exploring and exploiting are sort of directly at odds with each other. And so our goal, our strategy here is to determine what is the appropriate mechanism to actually balance exploration and exploitation. And so let's actually simplify. Let's just say there's a simple case of 2 slot machines over here. And these 2 slot machines have this payout range, and that range ranges from low to high over here. And after some number of spins, let's say you spun the left machine 10 times, it actually produces this payout range denoted by this green X over here. And we call this green X Q hat. And Q is, like we were saying earlier, is the sort of average reward. And Q hat is actually the estimate of the average reward of this machine. Like the actual true reward rate of this machine isn't known to us. Instead, all we know is based on this sample of 10 spins, the average or estimated reward is provided by this Q hat variable over here. And so this machine on the right, let's say we spun it 2 times. It also has a corresponding Q hat denoted by this green X. And you'll see over here that the machine on the right is slightly lower. And so the interesting thing here is that we don't know the true Q of either machine. And so we can represent the true Q actually as a normal distribution that's centered around the Q hat, right? And the width of this normal distribution is actually influenced by N. And so you can see on the machine on the right, because we just have 2 samples, there's far more uncertainty about the true Q level of the machine on the right. And that uncertainty is manifested as this wider standard distribution, wider normal distribution. And the idea here is that the lower the N, the less accuracy there is, and therefore the wider the distribution is. And so we can signify the width of this distribution by another variable that we call sigma. And so based on all of this, the question becomes, let's say we want to play the next coin, the 13th coin over here. Which machine do we pick? Do we pick the left or do we pick the right? If we pick the left, we might say we're biasing towards exploitation because we're focusing on the higher Q hat of the left machine. But if we pick the right machine, we might say that we're biasing towards exploration because the width of this normal distribution suggests that the true Q of the machine on the right might actually be higher than the machine on the left. And so what we do is we actually denote this thing called padding, where we take the Q hat and then we add some padding denoted by sigma, and we get these yellow X's over here. And what you'll immediately notice is that the yellow X for the machine on the right is slightly higher than the yellow X for the machine on the left. And that's to suggest that there's some likelihood that the true payout is actually higher for the machine on the right. So this padded yellow X actually reflects that the opportunity of uncertainty, let's put it. And so we call this opportunity of uncertainty the upper confidence bound, UCB for short. And so you can think of the UCB almost very similar, actually literally identically as a confidence interval in sort of standard statistics, where you have this random variable centered around Q hat, and the yellow X's, or the upper confidence bound, actually gives us an upper confidence interval for where that variable actually might be. So you may have heard of like the 95th percent or the 99th percent confidence interval. This yellow X is literally that. So we're essentially creating some padding, and we're picking the machine that has the highest UCB value. So that in this instance would be the machine on the right. And so let's do it. Let's spin the machine on the right. It actually ended up winning. And so we increased the N by 1. And because it won, the mean Q hat actually increased a little bit. It's still lower than the machine on the left. But then also, because the N decreased, the width of our standard distribution actually decreased a little bit. And therefore, the amount of padding actually decreased a little bit. But still, the UCB value, which is the yellow X, is still higher for the machine on the right. So we'll spin it again, spin it a few more times, actually. And you'll see we're slowly starting to win a little bit more. So now it turns out that the the mean Q hat for the machine on the right is slightly higher than the one on the left. And this process continues until we reach 17 spins on the machine on the right. And after 17, you have so much more information about the machine on the right that the normal distribution actually tightens such that the UCB value for the machine on the left now in this instance is actually higher. So this is when we switch back to the machine on the left, take a sample from it, and this process continues and continues and continues. And ultimately, it concludes with, at some point, at some arbitrary point, you can just stop the process. Here, I've stopped it arbitrarily after, 631 spins. And you'll see the vast majority of our coins were allocated to the machine on the right. And after this many spins, you can more or less really know that the confidence interval is really tight for both machines. And ultimately, this process of using the UCB instead of just using the Q hat or the mean allowed us to balance exploration and exploitation. And through that process, originally, if you recall, our first 2 spins for the machine on the right were actually suboptimal relative to the first 10 spins for the machine on the left. But despite that, we were able to balance exploration and exploitation and actually still infer that this wide standard distribution actually led to some semblance of opportunity, and we prioritized that opportunity, and then ultimately, after a while, benefited from that. And so this process naturally allows you to ultimately just trade off between exploration and exploitation. And the interesting thing here is that this process actually scales. So as you add more slot machines, not just 2, it can be 10, it can be 100, it can be arbitrarily many. As long as you simply select the slot machine that has the highest UCB value, you will inherently be balancing exploration and exploitation. Okay, so let's formalize this. We talked about the upper confidence bound, or the UCB. The UCB is simply the Q hat, which is the average or estimated payout based on the information that I have, plus some sigma, which is some padding to reflect the underlying uncertainty of my estimate in Q hat. Okay. Now, the next thing you'll quickly realize here is that sigma is just some fixed variable, and it represents standard deviation over here. But how many standard deviations of padding do you actually want to apply is the question. And so what we do is we actually scale this sigma by some constant scaling factor C, right? And you can imagine large values of C create more padding, which bias the system more towards exploration, and correspondingly low values of C reduce the amount of padding, which in turn bias the system towards exploitation. And so this value of C is actually like determining the quantitative trade-off between exploration and exploitation. And we actually have to determine this value of C empirically or experimentally. And there's no sort of one fundamental C that's correct in all contexts. Instead, the value of C is sort of problem or domain specific. So you can imagine that if you have a system where there's a lot of hidden opportunity, large values of C are actually well suited for that system, as opposed to a system where just a small number of samples allow you to quickly determine the true underlying Q values. Then low values of C are definitely encouraged. And so we have to ultimately determine this value of C. But still, this term on the right here, C times sigma, ultimately is just some padding that we add to the Q hat value to create the upper confidence bound. Okay, so with all of that in mind, let's get to Monte Carlo tree search. So Monte Carlo tree search is a form of stochastic tree search, which is just a big fancy word to say that it's based on simulations. And using simulations, you're able to determine what your optimal move should be. And so let's go back to our tree example. So we have our current position over here. And here I've described a go position, but this can also be a chess position or a Connect 4 position, or really any board game with perfect information. And again, we represent our tree. So here's all of the possible moves from this position. And our objective is to select from one of these moves. And so what do? We perform a number of simulations. And the terminology in MCTS, instead of the word simulations, we call them iterations. So MCTS iterations. And all an iteration does is simulate the game by picking a bunch of moves, and then that simulation ultimately reaches some terminal outcome, -1, 0, or 1. And then what we do is we keep track of the simulation results. And then at the end of performing a number of simulations, we look at all of the moves. So we see a number of simulations have gone through the move on the left, and then a number of simulations have gone through the move in the middle, and so on and so forth. And then we just simply pick the simulation with the highest average Q value. Or sorry, we pick the move with the highest average Q value after performing these simulations. And so let's now use our knowledge of the multi-armed bandit problem in UCB to actually guide the logic of our simulations. And so here's the process of an iteration. So the first thing we do is firstly, moves are just like slot machines. And so we can actually keep track of the Q hat n, which is like the number of times we've played simulations through this move, and sigma, which is, again, the standard deviation that's based on n. So we can keep track of these Q hat n and sigma values for every single position throughout the tree. And then we can perform a simulation, and that process starts off by starting with the top node. And then we look at all of the possible moves that we can play from this top node. And then we pick the move with the highest UCB value. And then we repeat that process. So then that becomes the current move, node. And then we look at all of its possible child nodes, and we pick the one with the highest UCB value. And then we repeat that process over and over and over and over again until we get to the bottom here, which is a terminal node. And a terminal node actually has a true or given Q value. So we know definitively whether that terminal node is a win, loss, or a draw. And then what we do is we do this process called backpropagation, which is different than neural network backpropagation, but confusingly, it's the same term. But really what all this is meant to indicate is that this Q value of 1, we effectively go back through all of the moves that led to this terminal Q of 1. And it's as if we hit a Q of 1 on all of these slot machines. So we change the Q hat values of all of the moves that led to this terminal outcome of 1. And then correspondingly, we increment the n of each of the moves. And then we go back to the very top. And then we repeat this process. Starting with the top again, we now pick the node with the highest UCB value. And because the last time around we picked this middle node, therefore its n is slightly lower. So its UCB padding value will be slightly lower. So maybe this next time around, we might pick a different move. And so effectively what ends up happening is each iteration walks a different path through the tree. And the paths are essentially guided by UCB. So we're trading off exploring new paths to gain new information versus exploiting old paths that might actually be more promising. And so that's it. And so it's a relatively simple process. We simply repeat this process guided by UCB. But if you think about it, we actually run into a pretty critical problem, and that's the cold start problem over here. So for the game of Go, for a given position, there's up to 19 by 19 or 361 possible moves. And so we call this in computer science trees a fan-out factor. So for a fan-out factor of 361, this is very, very large. And so when we begin all of our simulations, like all of our moves are equally lucrative. So all 361 moves are just as interesting to us. There's no basis for us to say that this move is better than that move because we have literally no information about any of the other moves. And so because we have no information, the only way to find information is by actually trying moves. And because of the fan-out factor of 361, you essentially devolve to breadth first search over here. So it's a pretty stifling issue. And so how do we actually solve this cold start problem? Before we get into the solution, here's another way of visualizing the cold start problem. Going back to our slot machine multi-arm bandit problem, when you first enter into the casino, for every single machine, we have n of 0, n equals 0 for every machine. So therefore, the Q hats are all the same, and the standard deviations are all really wide, and therefore the UCB values are equivalent, and therefore there's no basis for us to pick one machine over any other machine. And so how do we solve this problem? Let's use heuristics. So a heuristic is another fancy word, and basically all it is given a position, let's have some function that estimates what the Q value is going to be for this position. So what is the average win rate? Meaning if the Q value is high, close to 1, that means from this position, almost always we end up winning. Or if it's close to 0, almost always we end up drawing. So QEST is just the estimated Q value from this position. And then the other output of this heuristic function is called policy. So policy estimate. And the policy basically is a probability distribution over all of the moves from this position. And so for all 361 possible moves, we have a value between 0 and 1, where the sum of all of these values sum up to 1. So it's effectively a probability distribution. And the probability distribution represents the heuristics indication of how lucrative some moves are over other moves. So if we have this heuristic, going back to our slot machine example, let's say we have some scanner and the scanner is able to, I don't know, X-ray look at the internals of the machine, and it's able to predict with some level of uncertainty whether the given machine might be lucrative or not. And so here the scanner has told us that we have a 0.8 policy on the left and a 0.2 policy on the right. So again, these are probability distributions. So what we can do is we can actually scale sigma up and down based on this heuristic policy. And so because we got a higher policy for the machine on the left, we'll actually stretch out its sigma value. And then for the machine on the right, it was lower. So we'll squeeze its sigma value. And therefore, the UCBs are going to be weighted towards the machine on the left. And so this is effectively how we can break the cold start problem. We can start off with a heuristic that essentially influences or biases our sigma, and that causes us to focus our Monte Carlo tree search process initially based on the heuristics preferences. And so just to restate this, the UCB is larger for lucrative moves due to the higher sigma. Okay. So coming back to our old definition of UCB, again, it was Q hat plus this constant times sigma. This new version of UCB with heuristics is Q hat plus P times C times sigma. So P, again, is this policy estimate given by the heuristic between 0 and 1 that is essentially scaling up the sigma or the uncertainty level or the padding amount for our UCB over here based on this heuristic. Okay, so let's look at this again with heuristics. So first, we perform a traversal again. So we recursively play moves with the highest UCB value until we reach a new node. So here's a difference between the last time around. The last time around, we actually played our simulations until we reached a terminal node. This time around, we play our simulations until we simply reach a node that we've never seen before. So initially, when the tree is initialized, all you have is a root node. And so we first start off with this process of expansion. And so expansion is this process where we apply the heuristic on the new node, and the heuristic gives us an estimated Q and an estimated policy. And so instead of having a terminal Q over here, we actually use the Q from the heuristic estimate, and we back propagate this Q estimate up through the tree. So it's as if we, quote unquote, won the slot machines in this move sequence with the heuristic Q. And then for the children of this node, we use the policy from the heuristic to then guide future iterations of the Monte Carlo tree search process to bias towards moves that the heuristic policy ultimately prefers. And then we repeat this process. So we go back to the root again. We pick the child with the highest UCB value, and then we get to a node that we've never seen before. We apply the heuristic to that node. We back propagate the QEST from the heuristic, and then we bias that new node's children with the policy that was also provided by the heuristic, and then we repeat that process over and over and over again. And so what ends up happening, let's say after 289 iterations or so, at the very root level, we accumulate this Q hat, which is actually just the average win rate as we're performing all of these iterations or simulations. And again, this Q hat is going to be ranging from -1 to 1. And you can think of that as like, we try these 289 simulations, like what is the average outcome for these 289 simulations? It's given by this Q hat. And then also for each child move, we end up with an N value. So in the same way for the slot machines, we had N values, which is the number of time we played those slot machines. In this Monte Carlo tree search process, we have N values for child nodes over here. And that's essentially the number of simulations that played through this particular move, right? So for this move on the left, like we had 232 simulations that chose that route. Now, of course, each of these 232 simulations walks a different path down the tree, and each path leads to a different Q outcome or a Q heuristic outcome. But ultimately, at every node, we're keeping track of Q, the Q hat, and we're also keeping track of N, which is the number of times we visit that node. And then what we can do is we can actually transform these counts into probabilities. And so you can use any function, but let's just say like there's, you sort of make a linear combination to provide the sort of relative probability distribution weighted to 1. So we have 96%, 1%, and 3% over here. And these counts, these probabilities can actually be used to create a policy. And this policy is different than the heuristics policy because this policy is actually the consequence of playing many, in this case, 289 simulations. And so what we can say is that this QMCTS is actually a more robust or more accurate or refined output compared to the initial heuristic that we ran on this position. So the heuristic is just a single estimate. The QMCTS is actually the product of 289 game simulations. So we say that the QMCTS and the policy MCTS are actually refined versions that are more accurate than the original heuristics that ultimately ended up just guiding the Monte Carlo tree search process. Okay, so let's say that again. So we use heuristics that produce Q estimates and policy estimates, and those heuristics guide the MCTS process. And then the output of the MCTS simulations produces a refined QMCTS and a policy MCTS. So this is the big insight of Monte Carlo tree search over here. We use heuristics to guide our search or guide our simulations, and these simulations ultimately result in a refined, improved, more accurate version of Q and policy. Okay. And so then the big question becomes, how do we make a heuristic? And so for AlphaZero, they decided, let's just use a neural network. And so what they did is they took a Go position. Here, it's a Go position can be encoded in a matrix that's 19 by 19 by 2. And so you can actually think about this very, very similarly to encoding an image, where whenever we encode an image, we encode it pixel by pixel. And for each pixel, we actually have 3 channels of information that represent the red value, the green value, and the blue value of the pixel at that location. So very similarly, we have a 19 by 19 image, but instead of 3 channels, we have 2 channels over here. The first channel represents the white tokens, and then the second channel represents the black tokens. For a game like chess, it's actually a little bit more complex, where you have 8 channels representing all of the piece types. But for a game like Connect 4, it's still 2 channels, but ultimately every single square board game can be represented in matrix form, literally equivalently to an image. And then we can pass this matrix through a convolutional neural network. And this is literally the same architecture that's used for image recognition. I believe we use CNNs. We must use CNNs for image classification in products like Beacon. It's literally the same architecture that looks at pixel, quote unquote, pixel level data from the board. But instead of outputting classifications that we might output inside a beacon, for this, we're just outputting the heuristic output. So there's two outputs here. There's a QEST output, which is the estimated Q value from this position between -1 and 1. And then there's the estimated policy, which is the probability distribution over all moves from this position. And so we use a neural network. We encode the position in matrix form. We pass the matrix through the CNN, and the CNN outputs these two values, QEST and policy EST. Okay, so let's quickly recap, because there's a critical insight over here. So the heuristic is a function, right? Its domain, it's a mathematical function, right? So its domain is, or input is positions, and its range, the thing that it outputs over here, is Q estimates and policy estimates. Then we're able to use these heuristics to perform Monte Carlo tree search simulations. So the input to a Monte Carlo tree search simulation, again, is a position, a root position. And the output, after you've performed all of these simulations, is a Q MCTS and a policy MCTS. And so if you look at these two things, the heuristic, its domain is positions and its range is Q and policy. And then MCTS, it looks like its domain is also positions and its output is also Q and policy, except like we were discussing earlier, because of this exploration versus exploitation trade-off, we're kind of using simulations to optimally gain more information about the potential moves at hand, and therefore our Q and our policy are actually refined or improved versions of the original Q and policy estimates over here. And that's the critical insight over here. We can actually use the outputs of the MCTS process, so the updated Q and policy that are more refined, as training data to then train a new CNN that's going to be incrementally more accurate in its heuristic estimations. So this is crazy. It's like it seems like it's a self-reference, and that's because it is a self-reference, and it forms this closed loop over here where the heuristic produces better MCTS outputs. The MCTS outputs can then be trained to produce better heuristics, and then the better heuristics can be used to produce even better MCTS outputs, and this loops and loops and loops and loops. And so the visualization of this loop is MCTS uses the CNN to run simulations to produce refined Q and policy outputs, and then a new CNN is trained with the refined values to make better Q estimates and policy estimates. And this process can just ping pong back and forth over and over and over again. And this is the critical insight inside of AlphaGo and AlphaZero. They realized that this loop allowed them to train networks, train heuristics that just got incrementally better and better and better as a consequence of MCTS, which used this simulation or UCB or multi-armed bandit mechanism to gain more information about more and more lucrative subtrees of the game. But herein lies the critical question. If you have this sort of self-reference or recursive loop, how do you actually break the loop? So how do you bootstrap this system? How do you actually come up with an initial heuristic to start off this loop process? And as you think about this, like you might kind of say, let's come up with some sort of human intuition about what a heuristic might be. It turns out that the answer is actually much more simple. We can just literally start off with a randomly initialized CNN. Randomly initialized CNN is basically producing bogus heuristics, right? But despite the bogus heuristics, the MCTS process is able to refine those bogus heuristics to become incrementally better. And the incrementally better version can then in turn be further incrementally improved. And so what I'm trying to say here is that the base case of this recursive step is actually just randomness. So you literally start off with no intuition about the game at all, and you're playing more or less random strategy. But because of the mechanism of MCTS, you're able to hone in on some semblance of improvement relative to the heuristic, and then use the MCTS outputs to improve the heuristic, and then you're off to the races. And so this is what the training loop essentially looks like. So first, we start off with the CNN from the prior generation, or if we're starting off to begin the system, we literally start off with a randomly initialized CNN. So its weights are literally random. And then we perform the MCTS process of X iterations or X simulations of many, many games in parallel. So hundreds or thousands of games. We actually perform these MCTS things in parallel. And then the output of the MCTS is a policy. We can randomly sample from that policy. So play a random move guided by the MCTS process. And then once that move is played, we go back to step 2. We perform a bunch of MCTS iterations from that move. And then we randomly sample from that move. And that process continues and continues and continues until all of these games that we're performing in parallel ultimately conclude. And then basically the output of this process is for every single game, we get a sequence of moves that were played, or a sequence of positions that were visited in that game. And then for each position, we have the MCTS Q output as well as the MCTS policy output. And we take all of that data and we train a new CNN from the Q and policy outputs of the MCTS process. And then we take that CNN that we just trained and we promote it. And so it becomes the foundation for the next generation. And so we go back to step 1. And we repeat this process over and over and over again. And so here's how it looks for Connect 4. Here's basically the components you need. So first, you need some game logic. So you need to be able to represent the position, the state of the board, which pieces are where. You need some logic to represent what moves are actually legal from what positions. And then you need some logic to determine whether a position is a win or a loss or a draw. From there, you need some MCTS structure. So you need this game tree that keeps track of the Q hat, the N, and the sigma values for each node in the tree. Then you need some self-play logic. So logic that actually performs the MCTS iterations in parallel for many, many games. And then you need a CNN, which is the network that's actually performing the heuristics. And then finally, I kind of alluded to this earlier, you need some mechanism to determine what the optimal value for C is. So C, again, is the exploration constant that weights our sigma value. And there's other factors that you need to experimentally determine as well. So you need to determine how large your neural network is. Like how many layers does it have? How many parameters does it have? You can imagine too large of a network it isn't going to be effective because there's not enough training data to train it. And correspondingly, too small of a network isn't going to have enough free parameters to be able to take in all of the rich information that we're determining from this MCTS process. So you actually have to experimentally try a bunch of these values and see what the best results are. And so this process is called hyperparameter sweeping. And so I implemented all of this in Python. And what I very quickly found is that Python is a great language, but it's not so great for CPU parallelism and memory usage. First of all, objects in Python tend to take up a solid amount of space. Like Python has to keep track of the type of each object. It's not statically compiled and so on. So I was running into out-of-memory issues on my machine as I increased the Monte Carlo tree search iteration count or the game count. And then also, Python is really bad at CPU parallelism. And that's because it has this thing called the global interpreter lock, or the GIL for short. And basically what this means is you might have multiple threads in Python, but only one thread can be executing a single Python instruction at any one time. And that happens by allowing the thread to capture, the global interpreter lock, or the GIL, and then that thread can continue executing instructions effectively until it reaches a point in the code where it's blocked on IO. And once it's blocked on IO, it frees the GIL so that other threads can execute. So if you have, for example, like a multi-threaded web server, like I believe the paired tutor backend is written in Python Django, I believe. And so multi-threaded Python is fine for those environments because when you're running an HTTP server, you're for the most part blocked on I/O. Whereas for this use case, I wasn't blocked on I/O at all. Like I wanted all threads to be computing, doing win-loss draw checks, doing move validation checks, and then performing the Monte Carlo tree search process all in parallel. And so I kind of hit a brick wall on this on Python. And so I did what any reasonable engineer might, and I rewrote it all in Rust. I really wanted to learn Rust, so this was like a nice 2 birds in 1 stone. And so I moved all of the game logic, the Monte Carlo tree search logic, and self-play logic in Rust. And Rust actually has fantastic support for multi-threading. If you haven't learned Rust and it's sort of been on your periphery of things to learn or check out, I highly, highly recommend checking it out. It's a fantastic language. And what I was able to do also is keep the neural network logic in Python. So the CNN stuff remained in PyTorch. The hyperparameter sweep logic remained in PyTorch. And I use this library called Py03, which has some really nice bindings between Python and Rust. And what this allows you to do is expose a Python function that you can call in ordinary Python world that ultimately underneath the covers calls a Rust function, which can then take advantage of the underlying threading and parallelism structures that exist in Rust. And so with Rust, I have really tight control over the board representation. I actually just used what's called a bit board representation. So each little cell inside of a Connect 4 board can actually just be represented with 2 bits, right? It's either empty, it's either player 1 or player 2, right? So there's 3 states, so I only need 2 bits to represent a given cell, right? So I literally packed that information into 2 bits, which allowed me to store the entire board state in 6 to 8 bytes. And so that compact representation of the board state was really useful from a memory perspective. And then the threading primitives were really useful in terms of allowing me to run all of these game simulations in parallel. And so the game simulations happen in parallel, but then they call the Python neural network to perform the heuristic outputs of Q estimates and policy estimates, and then it sort of ping pongs back and forth, and it all works. And so here's the results. Here's training 10 generations over here. And the nice thing about doing this on Connect 4 is Connect 4 is actually a solved game, which means that any position is definitively known to be a win, loss, or draw. And the optimal move that wins in the fewest number of moves is actually definitively known. And so what I can do is actually check the output of my MCTS process, the policy outputs, against this solver and objectively judge the accuracy of my MCTS outputs. And so that's essentially what I did over here. So this green line is for each generation, what is the probability that the MCTS output actually prefers the optimal move according to the solver. So you can see each generation, it improves. And frankly, I got to this point and it was amazing and exhausting, but it was just so anticlimactic because I was just seeing the numbers just go up and to the right. And it was like all weird and abstract. And so one other thought here is that the CNN is actually pretty small. There's only 7.3 million parameters. Now this is quote unquote small relative to, you might think of large language models today, which have hundreds, tens or hundreds or even trillions of free parameters over here. So this is relatively tiny neural network. And so I decided to actually just build a terminal UI just for kicks. And so you can play Connect 4 against a neural network that you can train. And you can see what the actual policy outputs are of the MCTS process. Here you can see there's 1,400 iterations that have been performed. And it prefers these moves. And it gives you the evaluations and the win percentages over here. And all of this is available on GitHub. It's all nicely commented. And so if you want to check it out, I think it's a good code base to see how CNNs work in this context, how Rust multi-threading works, how MCTS works. and so on and so forth. So I encourage you to check out the code, and you can train a brand new Connect 4 network on your MacBook or laptop in a matter of, I don't know, like 30 minutes or so, and you can play against it in your terminal. So I had a ton of fun with this project. It was one of the first or few projects that I've truly completed all the way up until the end, and I learned a ton. To me, it was really exciting because it sort of showed firsthand how a seemingly mechanical deterministic system, which is an algorithm or a program, can simply just execute or spin, and in the process of execution, actually learn in the same way that we as humans might think of as learning strategy. And to me, this has some pretty profound philosophical consequences. And frankly, the reason that the DeepMind team and a lot of these AI research labs are focused on these quote unquote game problems like this is because they're actually simplified versions of what we want these AIs to do in a more open-ended context. So you can imagine any problem that we're trying to solve as humanity can be structured in principle in a way where there's this Q value function, which is supposed to represent the things that we actually care about in a particular context. And that our system also has a set of rules, and it also has a state. And based on the state, you can perform a number of actions according to the rules. And then the actions influence the state. And ultimately, over time, that reaches to these outcomes, these Q value outcomes. And so we can think of these AI systems as trying to learn the mechanics of our world, our universe, or these games, and develop strategies to actually optimize the things that we care about as humanity. And so this process is actually called reinforcement learning. It's just a general category of ML where the training data isn't necessarily given beforehand, and instead, what we do have instead is like a value function that's supposed to represent the things that we care about, and we sort of unleash the process of exploration to determine what is the best mechanism to optimize the outputs that we care about. So the reason that these AI labs started off, I think, with games like this is because they wanted to show a proof of concept that this sort of mechanical structure is able to generalize and learn. And I just found that to be remarkable, and I found it incredible that you could just do it in just a few hundred lines of code on your MacBook, and inherently it's the same structure that for Connect 4 as it is for all these board games. So I had a great time. It was amazing. I hope you enjoyed it. Maybe with that, I will turn it over to you all. Feel free to ask any questions you might have. Thank you. Brian.
I had one comment and one question. The comment I had is, if I recall correctly, when AlphaGo first came out, I thought it was really interesting how the bot was actually playing in some cases against the intuition of humans that we've built over like thousands of years. And so it was cool how like the humans actually basically the metagame had shifted after that, and then like we learned that, oh, there are things to explore outside of like what we had already considered as like the standard, which I thought was really interesting.
100%. Like Lee Sedol's quotes about this, like he described it as like this alien thing that it's just like crazy moves. And for those of you who play chess, like you can for sure relate to this experience. Like when you turn on the chess engine and see some of the moves that it plays, they're absolutely ridiculous. Like no human would ever think about it. But once you see the logic, you're like, oh, okay, I get why this makes sense. And so I think a very similar thing happened to Go. And to me, I think that generalizes really to any problem that we're trying to solve as humanity. Like our human intuitions about these problems ultimately guide us and bias us, perhaps in situations that lead us to suboptimal results. And the optimal result might actually be beyond our capability of initial understanding. And that's where AI assistance actually becomes super interesting, because I think it's able to pierce through the boundary of human limitation and actually produce solutions that will eventually recognize as desirable and optimal, but simply couldn't get to. And the fact that this has definitively been borne out in the context of these games already, to me, is an indication that it's going to happen many times over in the future ahead of us.
And then the question I had was with regards to the initial heuristic, because you mentioned that we could just start with random, and I was just wondering, I would assume that by starting random, there's a little bit more of a warm-up time to get to like reasonable states. I was wondering, like, how significant is that in practice, or is it usually pretty negligible?
Yeah, so what I'm able to see, so I've done like hundreds or thousands of training runs at this point, and I'm able to see the sort of general patterns. It seems like after generation 4 or 5, every single starting point ultimately reaches the sort of same threshold of capability. But the first few generations, it definitely flounders. Like there's some instances where it actually regresses. So it'll actually play worse after a training generation, but then it quickly rebounds. And so what I discovered is like the starting point actually doesn't matter. And I think if you really think about it, as long as you're iteratively improving reliably through each generation step, then it's just a matter of doing more generation steps to get to whatever target goal is. And the interesting thing is for AlphaZero and AlphaGo, they actually at some point just stopped the process. And that's not to say that it couldn't improve from that point. It's just that they said that we know that this thing is just going to keep improving. And they just decided to stop wasting CPU or GPU hours to just incrementally training it more, because like, what's the point? So I think the sort of meta point of reliable improvement is the key idea over here. As long as you reliably improve, it doesn't actually matter what